Electrons are ejected from a photoelectric surface with a maximum kinetic energy of 1.92 times 10. So I'm going to put E max, EK max, just to make sure it's super clear. EK max is equal to 1.92 times 10 to the negative 19 joules. If the incident light has a wavelength of 4.10 times 10 to the 2 nanometers, convert that to meters. And we're looking for our FO, is our threshold frequency. Now, I converted nanometers into meters. Now, which H you use is important. Since we have joules, you need to use the H that has joules in it if you're using this energy. If this energy was in EV, you could use the H that has EV. So just be mindful of that. If you start with a given amount of energy in units, you need to use the H that coincides with it. So let's set up like our overall formula based on conservation of energy. Okay, because this is involving multiple things. So based on the conservation of energy, our energy coming in, that's incident, I'm just going to call it E in, like incident, is equal to the amount of work required plus EK max. So how much energy the electrons have when they're shot out. So now I'm going to expand what I know about each of these things, okay? So actually first, no, I'm not going to, yes. So E incident, I can find the energy of that using just my energy formula of light, okay, from our atomic physics section there. Now, I know work is H times FO. And I don't have to expand EK max at all because I'm just given it as a numerical value. So it would be redundant to do anything else with it. If, say, I was given speed, my EK max I could expand into half mv squared. Kinetic energy, right? So what we're looking to find is this, the FO. So let's isolate for that to start with. So right now, I want to isolate for this part of the formula. Right now it's added to EK max, so I'm going to move my EK max over. So now I have HC over lambda minus EK max is equal to H times FO. With me so far? Okay. So let's just put in all of this information because we know all of this right now. C, so look on your back where you have all your constants. Find C in the constants here. Yeah, C is the speed of EMR, right? So it's frustrating because you would think it would be a V, right? But it's a constant, and so they label it as little c, okay? So yeah, good question. So let's put in what we know here. So let's use our H that has our joules in it. So we know that H needs to be 6.63 times 10 to the negative 34 joules times seconds. And I know my C is 3 times 10 to the 8 meters per second. So So I'm just writing those things down because we didn't have them when we started, because we didn't know we needed them. Okay, so let's put that in. 6.63 times 10 negative 34 joules times seconds times 3 times 10 to the 8 meters per second divided by 4.10 times 10 to the negative 7 meters. Minus, and I was told my EK max, which is nice, so that was 1.92 times 10 to the negative 19 joules. This is all equal to H times FO.
And you don't solve for FO?
Yeah, we are. I'm just doing it, like, I guess you could do all of this and then go divide it by FO, but I'm just doing it in 2 steps. You can do it differently than me.
Divide by H.
I mean, yeah, divide by H. Yeah, I'm just going to do that second, because then I make less mistakes. So did you put this in already?
Yeah.
What'd you get?
Oh, never mind.
2.9312 times 10 to the negative 19.
Nice work. And that would be in joules. Okay. So now our FO is equal to 2.9312 times 10 to the negative 19 joules divided by our H. And again, I'm going to use my H that has joules in it. Okay? So 6.63 times 10 to the negative 34 joules times seconds. So see here, look, joules cross off, and I'm left with 1 over seconds, which makes sense because it's frequency. It's hertz. I know. I'm excited about it. So our FO then is 4.4211 blah blah times 10 to the 14 hertz. Sig digs 4.42 times 10 to the 14. Hooray! We did it. Let's do another one.